Hello again, everybody. So I'm going to run through a couple of the Khan Academy sections that you had for this chapter and try to help you understand them a little bit better. So these are all going to be exponential equations, which have a general form where we have some starting amount right there. And then this, the thing under the exponent, is called the rate. So that's going to be the percentage that we're growing at. Specifically, this is the percent growth. Sorry, let me try that again. 100 or the 15 right here. So if I rewrite this, try to do this 100%. When you have 100% of something, you have exactly what you have. So 100% of 5 is 5. It's no more, it's no less. What this is an extra 15% that's being added on. So when we think about percentages, we can get rid of this percent sign because the word percent means per 100. Per is another word for divide. So dividing by 100 does this. It moves your decimal point left 2 places. And if you think about this, multiplying by 1 over and over again would just stay 5, right? 100% of 5 is 5. 100% of 5 is 5. 100% of 5 is 5. It doesn't ever change. It's just itself. But when we add on an extra 15%, what we would get is 115%, obviously. Oh, that's not a percent. That's not a 5. There we go. 15%. Again, if we move that decimal left 2, boom, boom. Sorry, it's kind of sloppy, but it's the 1.15. That's where this number is coming from. Is it's saying that you have 15% growth every t, which t is, it doesn't tell us. Oh, minutes. As a function of minutes. So t is time and minutes. So every minute, there's an extra 15% growth in the area that's apparently being damaged by a fire. So it's growing by 15% each minute. So this equation right here has, again, 2 main parts. The beginning amount. What does 5 represent? 5 is the amount of area that we have when we start out. It is the starting amount, and it gives the area in square meters damaged by fire as a function of minutes. So this is what's happening over and over again. It's growing by 15% repeatedly, and this is the starting amount. So that's the amount of area that we started out with. What does 1.022 represent? So this is going to be the rate. So expression 11 times 1.022. So by the way, again, if I move my decimal back 2 places to the right, it would actually be 2.2%. Don't get confused by the difference between that number and 1.22. This would be 22% growth. This would be 2.2% growth. So just over 2% growth. So models the gross domestic product of the U.S. in thousands of dollars as a function of numbers of years since 1950. So every year, every T is this in this problem, T is a year. The GDP, the gross domestic product, increases by 2.2%. So what does that represent? Nope, it's not the starting amount. The starting amount was 11. So in 1950, apparently, the gross domestic product was in thousands of dollars. So $11,000, that seems really low, but okay. The max, no. Per capita GDP, the per capita GDP in the United States multiplied by approximately 1.022 each year. Yes, that is what's happening. It's getting multiplied by that each year, over and over and over again. This expression, what does 60 represent? 60 is going to be the starting amount. So models the number of nano-related patents granted in the U.S. as a function of years since 1991. So in 1991, there were 60 nano-related patents. Yep, right there. There were 60 nano-related patents in 1991. Because again, this is the beginning amount, and that's the rate that's changing over time. Hooray! All right, that's it for this one. Keep practicing. Hopefully, this one isn't too tricky for you to get into, but try it over and over again until you really understand how these different parts work together.